All right. We had kind of a quasi snow day. Class was canceled, or the university closed in the middle of class yesterday, and a lot of you weren't there, which, I don't blame you. It was pretty nasty out there. And the strange thing was, north of the river, it wasn't near as bad as it was when I was going south of the river. And when I left to come to class yesterday, that would have been Tuesday, February the 20th. I, uh, I almost turned around and came back, but I was like, man, there's going to be about 40 or 50 students sitting there, and that's about how many there were out of 130. So I was glad we got together, but basically all we did was we looked at homework problems. It's setting me back a day. Well, who cares? There's some things that we can drop, and I'm learning more and more about this expert TA as we get into it. That the problems are tricky that I assign, because I just kind of like read the first couple sentences and I go, oh well, that's not bad. That's an okay problem. But anyway, so I'm going to do the problems that we did in class for those of you who weren't there, so you don't miss anything. And then I'm going to go into then I'm going to give a new lesson over the end of chapter 6. And the exam will cover just chapters 4, 5, and 6. I think that's enough on our plate for the exam a week from Thursday on March 1st. Not this coming Thursday, like I said in the thing. I don't know what. For some reason, I was thinking all day yesterday was Thursday. I don't know why. Maybe, I don't know. So anyway, here we go. The first one we did was the skier problem, and I'm going to try and do the work over here on my ladybug. All right, so here, let's call her up, and I probably should. And I'm going to do like one problem per little segment here, because each one will take about 7 or 8 minutes to do probably. All right, so can I magnify that sucker? I think we need to magnify that quite a bit. There we go. Still need to magnify it. Sorry. I should have gotten a little bit more prepared. There we go. All right, so it says a skier heading down a slope. All right, I'm just in 9.5 degrees, and we found that there's certain things we know. We know that we're assuming the skier's here on Earth, so the gravity is 9.8 meters per second squared, and that's all we know. We have no mass, and we know that mu of k is equal to 0.10, and that's it. Okay? So we wanted to find out what his acceleration was. So the first thing you always do, of course, is you draw a picture. Here's our skier. That's a huge 9.5 degrees. I was watching Lindsey Vonn yesterday ski down when they actually got a good camera angle of where they are at the starting gates of the downhill. That's like a 70-degree drop. It's the damnedest thing. I was like, oh my God! It just kind of put my heart in my throat just to see from television. All right, so here he is, and he's going downhill. Now he's got a normal force, and he's got a gravitational force, and and a frictional force. Those are the only three forces that are working on him. So we'll make him flat. We'll rotate this down, plunk, make it flat so it looks like this. So now it looks like the skier is going this way. Okay, he's accelerating this way, and gravity, all of a sudden, the gravity vector goes like this, where this is the x component. This is an positive x component of the gravity. This is a negative x component, y component of the gravity, and the normal force looks like this, and the frictional force looks like this. All right, so there we go. So we just take the sum of the forces in the y direction are equal to 0. And one of the points that I made is anytime you have something slanted, the x where they're sliding, okay, where they're sliding, the x component in the positive x direction, if it's a sliding block or a ski or anything like that, the x component of the acceleration is always g sine of the angle. Okay? that is an x component of that's one of the components of the acceleration. The other we're looking at y, but the other component of the x component for this one is we actually have a frictional force. All right, so we've got in the y direction, we've got the normal force. He's not accelerating in the y direction, or she, not at all, minus this component, which is g mg cosine theta. So we've got minus mg cosine theta, which is equal to, so the normal force is equal to mg cosine theta, which is where we also find the frictional force. I know it's in the x direction, but the magnitude, this is where we can find the magnitude of the frictional force, is equal to mu of k times the normal force. That's the formula for it. And if the normal force is equal to this, it's mu of k times mg cosine of theta. All right, so now we look at the sum of the forces in the x direction, which is what we're trying to find, is what is his, he is accelerating in the x direction, and we've got mg sine theta minus mu of k mg cosine theta. All right. Okay. All right, so now, sorry, I was having a moment. I was going, oh, this is going to work out just fine. So we get MAX, which is what they're after here, is equal to, let's write it bigger, mg sine theta minus mu of k mg cosine theta. Now look what happens. Look what happens here. The ends all cancel. So I've got AX is equal to g sine theta minus mu of k g cosine theta. Whatever your theta happens to be. That's the way that works. Now, this is a good problem. It says find the angle of the slope, and which could coast at a constant velocity in degrees. In other words, it's just going to coast at a constant velocity. Well, what does constant velocity mean? Acceleration is equal to 0. So let's set that AX equal to 0 and then use the same formula. So we're going to wind up with G sine theta. We're trying to solve for theta. G sine theta minus mu of K G cosine theta. All right. Just looks good. Looks like we've got mu of K G cosine theta is equal to G sine theta. All right. And so that cancels and that cancels. And so we get mu of K is equal to the sine of theta over the cosine of theta. What the heck? Ah, but we know that that's the tangent of theta. So the actual angle, and this is kind of a cool little thing, the actual angle is equal to the inverse tangent of mu of k. Because we said mu of k is equal to the tangent of the angle. And that's one of the ways that you can, just to let you in on something, I'll show my mug up here on something. When we want to show a coefficient of kinetic friction of something, all right, so here I've got my calculator in this. Do I got it flat? Yeah, so if I tilt this up, okay, right when that started to slide, when I get that angle, it keeps hitting something over here. Once it, oh, it hits this thing. Anyway, when it starts to slide at a constant velocity, so there you go. And I'll make sure that you get that this is put on the thing. So we're done with that problem.